Guess what happened? I messed up. I've typed some things wrong in the math functions, and I did this tutorial out, and it took like 20 minutes, or like 30 minutes actually, and nothing was working, and I finally figured out the problem. I wasn't paying attention. I was talking too much. So this is the old line. You're going to want to change this to line.1.x. Rise over run, not rise over 0. So that should help with some stuff. So that's the first thing. I'll keep that there in case I need to redo this tutorial again because I say something. And then we have this one here that I also messed up, where this should be x root 1. It used to be x root 1 and x root 1, which is the same line as here, when we need to be comparing x root 2. So make those changes and we should be good to go. So I want to make this tutorial speedy, and we got a lot of work ahead to do with this wrapper class that I really hate to have you guys do, but we have to do it. Basically, we need a container that contains a lot of data for us about each point, so let's get to it. It's going to be called curve point. Create that class, if I can type, and then so it's going to require a lot of parameters in it. So we got public double x, we got public double y, we got public double move speed, public double turn speed, we got public double follow distance, public double point length, we have public double slow down turn radians, we have public double slow down turn amount, and that should be good. Now we're going to make a first constructor, public curve point, double x, double y, double move speed, double turn speed, double follow distance, double slow down turn radians, double slow down turn amount. Okay, and we're basically just going to set all those things. So bind constructor parameters to fields, select all of them. We don't have time to do that manually. There we go. The first time I typed it all out, and it took actually like 6 minutes by the time I was on this wrapper class, but I don't want that to happen. So now we need another constructor. This one's just going to take in one thing. It's going to take in a curve point, and it's or this point. Come on. Okay, so we have to be worried about copying and pass by reference in Java. We have this problem that anytime you want to modify a curve point, and you think, oh, I'll just create a new one, curve point, modified curve point equals a curve point we're going to modify, and then we can modify it. Well, no, you're wrong, because we have an alias that's set up. When you set in Java equals, that's only setting the pointers equal to each other, so you have an alias. They're actually the same memory location. So that's all we're avoiding here. Is we're creating an alternate constructor that does the copying manually. So I wonder if IntelliJ can do this. Nope, it doesn't know how. So okay, x equals next point dot x, it's this point dot x. Same thing for y equals this point dot y. Move speed equals this point dot move speed. Turn speed equals this point dot turn speed. Then we also need follow distance, same thing. Then we also need slow down turn radians equals this point dot slow down turn radians. Then slow down turn amount equals this point dot slow down turn amount. And finally point length equals this point length. Great, we got our wrapper class, and it's only 4 minutes, 2 minutes faster this time. Okay, so now we can go into our robot movement. We get to finally write the most beautiful part of the pure pursuit, which is get follow point path, and then we'll be using it. So basically we have a path, we have our robot location, and what pure pursuit does is we need to return an instantaneous follow point. That is basically, at this moment in time, what point in space is our robot heading towards? or really a relative vector, but yeah, what point in space relative to us are we going to go to? So that's the method we're going to write now. We're going to have to go through all the points, and we're going to have to write some logic, but here we go. So public static, and it's going to return a curve point because it's getting a point, get follow point path. And in it, we're going to pass an array list of curve points, and we'll call this path points. A double X pose of the robot, double Y pose of the robot, and finally a follow radius. Great. So we're gonna initialize just blank before we even do anything. Follow me. This is what we're gonna return. It's just gonna be a new curve point and path points dot get 0. So it's by default going to go to the very first point in the path if it doesn't have any intersections. You guys can improve upon that. I just want to show you the core algorithm. There's a lot of improvements that can be made. In fact, the code I'm working with is like pages and pages more lines than this, but it's just for all those edge cases, and they really don't really matter like 99% of the time, but we just want to be extra careful. But so okay, so now we're going to go through all the path points. I equals 0, I is less than path points dot size minus 1, because each time we're looking at a line, and a line is defined by 2 points, so we have to stop one early. So curve point start line equals path points dot get I. Curve point end line equals path points dot get I plus 1. And so we're just getting aliases to that. We're not modifying any data. Basically, these are just pointers to the memory in the list. So now we get to call our beautiful method that I just fixed after I messed up in the tutorial. It's going to return an array list of point. That's all our intersections. So I guess we'll call this intersections equals line circle intersection, and it's going to take a point x, the robot's point, so x pose y pose. You know what? Let's be consistent. Let's make this a point robot location. So then we can just pass that in here. Less characters, way better. Okay, so then we got our follow radius, new point. Yeah, we have to do, or we can do start line dot 2 point, or dot point. Oh, I didn't make that constructor. So let's do that. Let's go into curve point, and let's say public point 2 point. Basically, all this is it's gonna convert our giant point to an OpenCV point, and curve point, and this is actually can be static. Oh wait, no, we can call. Actually, no, it's just gonna return ourselves. So this dot return new point x comma y. There we go. So now we can use that in a lot less characters. So start line dot 2 point. We got then the end line dot 2 point, and that's gonna find now all the intersections that our circle extended at the point of our robot is gonna have with all the path points. Now you might be thinking, wait, Peter, there's 2 intersections. Well, you can, if you're with a line, you can have multiple intersections. You can even have many if you have a full path. Well, so now that's what we have to do. We have to evaluate which of those many points is going to be the best one to follow. So already by iterating in this order, we're preferring the points that are later in the list. So more progress, more closer to the end point. Well, not necessarily closer, but like closer in order to the list, to the end point. So whatever we set the follow me point will be the last. It'll be set by the last time it goes through this loop. Well, the last time we have any intersections. So basically the order sets the priority since we're iterating from 0 to path points that size minus 1, that sets our priority. The second priority we're going to have is we want points that are closest to our robot's angle. That's going to weed out the choice between the 2 intersections. If we have, let me open up Paint here. If we have a path like this, and say we have a circle and there's 2 like this, you see there's 2 intersections. Well, then say our robot's facing like this way, then we're going to follow this point because we're just closer to it. So yeah, we'll choose the one that's closest to our angle. Okay. So to do that, we're going to define a double closest angle equals by default a really, really big value. I mean, angles can only be within a certain amount. So now we're going to go through all the intersections. This intersection in intersections. And we're going to get the angle from our robot's location to this intersection. So math.a102. Use a102. It gets the right quadrant for you. Dot y minus world y position, and this intersection dot x minus world x position. There we go. Now, well, that's the, oops, I don't know what it's doing there. Well, that's the absolute angle to it. So say our robot was here, and here was the point we're getting to the angle. That's the absolute angle on a world coordinate space, but say our robot was already faced there, we should probably return 0. So, okay, well, so we'll do our subtract angle method that we wrote. So double delta angle equals math.absolute, because we only care about magnitude, math functions dot angle wrap, because we need an angle wrap. We don't want really, really big angles when it shouldn't be like that. And we're just putting angle minus our current angle. So that's our delta angle. That's say these angles were the same, this would return 0. If we were a little bit off from that angle, then we'd start to return a positive value because we're using the absolute value. Great. So now, if our delta angle is less than our closest angle, whoops, delta angle is less than our closest angle, then we're going to say closest angle equals delta angle, which is an absolute value, which is what we need. And finally, follow me dot set point this intersection. Bam. Whoops. Do I not have a set point? Oh yeah, we need a set point. Okay, create setter. And all we have to do is say x equals point dot x, y equals point dot y. Beautiful. Now we found the point point on the path, that could be anywhere, that we're currently following. So now we can say return follow me. Great. That's the core of the pure pursuit. Now all we have to do is use it. We're almost there. Bear with me for this last function. And here we go. So let's go to follow curve. Okay. Once again, I'm really simplifying this. You guys can add a whole bunch more logic to make this better. But I want to just show the essence of pure pursuit, not all the flares and edge cases that we put in our robot. So public static void follow curve. And it's going to take in, once again, the array list of curve points, and we'll call that all points. And our follow angle, that I, for some reason, need to be 90 for me to feel secure. So then, one of the things that the debugger does nicely is we can just, we can display these lines for debugging purposes. Should you have any issues, it's always a good idea. So we're going to go through all points.size -1. You guys don't have to do this if you don't want to, but I highly recommend it. Computer debugging.send line. Now this class is in the repository that we cloned, the last one. So new float point. I'm just gonna copy and paste this in. You guys can pause the video. This is just for debugging. I don't feel bad about it. So just copy this line here, and that's what it's gonna do. It's gonna send the information from our program to the debugger so we can display it visually. And I totally want to see that. So okay, now we can say curve point follow me equals get follow point path. We're just calling our method all points, and new point world x position, world y position, because it wants our robot location. And finally, all points dot get 0 dot follow distance. So this is a task for you guys. I left this undone. All these different points, depending on where you are, have different follow distances and characteristics. Right now, we're pretty much using none of them. We're just using the first follow distance and the first all the attributes. So one of the things that you can do is you want to write a function that, given it's going to using a list of path points and a path, it's going to take where the robot is and figure out where you are in the path. And basically the way I've done it is I take the point perpendicular to this line, so it looks something like this, and passing through the robot's point, and then I take the intersection here, and then I choose the point ahead of that one on the line. I know it sounds like a complicated complicated task, but maybe you just want to use you could also say our current point is, or like the current point is like the one that's closest to your robot location right now. That's another good option, but it has some flaws. I like this method a little bit better. So that's up to you. I'm not showing you guys how to do that exactly, but basically this follow point will not always be this with this follow distance. All right, so if you want to write that, that would be a good option, or you can just stick to the tutorial. It's all up to you, and just use a consistent follow distance. So now what we're going to do is we're going to say, just for debugging, once again, it's always a good idea to display stuff. We're going to send key point, new float point, follow me.x, follow me.y. I have so many point wrappers. I don't care, whatever. So now finally we get to do it. We wrote it. It was the first thing we did. We get to call go to position, follow me.x, and I'm not using points here apparently. Follow me.y, follow angle, which is passed in here, which needs to be like 90 by default. We got our preferred angle. Oh wait, movement speed, silly me. So this would be our follow me dot move speed, our preferred angle, and finally our turn speed, follow me dot turn speed. Yeah, we did it. We wrote pure pursuit. Well, at least I think we did. Let's try it. So now we can go finally to our where is it? Where's my op mode? There it is. And we're gonna add, oops, I've already done it here. Now we can finally delete this. We can say array list. This is all we have to do to even use pure pursuit. It's very nice syntax now. Array list of curve point, all points equals new array list. All we have to do is say all points dot add new curve point, x, let's say 0, 0, move speed, let's say 1, turn speed 1, follow distance, I guess I usually do use a follow distance around 50 centimeters or to 80 centimeters. The faster I want to go, the more follow distance I do, but keep in mind that's more rounding of the position. So let's do slow down turn radians. I don't think we even use this, so if you want to implement it, basically what this does is it will slow the robot down while we're not, if we're too far away from our target angle. So let's set that to like 50 degrees. It will stop moving, or go, in this case, stop moving because I put in 1. You can tone down that effect. And there we go. Let's copy and paste this in. You can put more attributes, but all my follow distances are just going to be 50 centimeters. So let's put one in, I guess one midway through the field, which is about 180. Let's put one at the end, so 360. Yeah, let's do 360, 180. Let's do like 220, 180. I guess then we can do like 280, and let's start moving down. Let's go like 50, and then finally let's go like I guess we can do 250. We can go even a little bit back to 180 maybe, and 0. Now we can finally call it follow curve. Make sure to import that all points 90, because I don't know why, and let's put that in. And okay, so let's put that in. Let's hope and pray, and something weird's happening. But yes, pure pursuit, and it's messing up at the end because I can talk about that in a second. But we got it. We did it. I might be sending it with someone else, but yeah, that's it. We did it. Okay, so you're gonna be like, whoa, 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 what's all this crap at the end? Well, that's the problem. That's a problem that I'm gonna leave again for you guys to fix. I'm not showing exactly the math behind it. Basically, since you're looking ahead, now it has no more line to go at the end, so we have this problem. So what I've done in most of our Pure Pursuit robot locations is we actually will just extend this last line by a little bit more than the follow distance, just to be safe, and I'll still go to this point as a final target point, but I'll be pointing to the extended path. So imagine there's a circle here, then the circle will intersect with the extended path, and we'll still get that continuous motion at the end there, as opposed to this. Other than that, I think that's all I'm gonna cover for now. Oh, and another thing is that if you want to notice that once the circle stops intersecting, it doesn't even go to this point. So you want to put in some logic that once we get pretty close to the target point, you want to just set the follow point to the last point in the list, and that's all you have to worry about. And so I guess that concludes the Pure Pursuit series. Thank you guys so much for watching. Let me know if you have any questions. I'd be happy to answer them. And I guess, wow, I didn't think I would be able to finish this in 5 tutorials. I guess I just really, I like did multiple takes on a couple of them. Wasn't really happy about how they were looking. And I mean, this is still pretty crappy at the end, but come on, this is like, this is some basic logic, can fix that up, and you'll be getting smooth motion. Just look at that. Look at that nice curved path, and you specified this random amount of this almost random points, and it's rounding it. Very useful. I think I did a good job. So thank you guys for watching, and bye bye.